as I mentioned, the idea of orthogonal matrices leads us to an interesting factorization. What do we mean by that? It's an interesting way of splitting a matrix, a certain kind of matrix, into the product of two other matrices, both of which have nice properties. So what is this interesting factorization? Well, we're going to look at invertible matrices. So let's say that this is an invertible matrix. Then we know that its columns have to form a basis for Rn. If it's invertible, it means that the columns are linearly independent. There is n of them, so they must form a basis for Rn. And that basis can be changed into an orthonormal basis by using the Gram-Schmidt process, right? So I can start from this matrix, look at its columns, think of them as a basis for Rn, use Gram-Schmidt. From there, construct another matrix which is going to consist of orthonormal vectors and therefore make up an orthogonal matrix. All right. So let's call Q this orthogonal this matrix. Okay. So the Q is the matrix that consists of the orthonormal columns obtained from the columns of A by using the Gram-Schmidt system. Process. Okay. Then Q has to be orthogonal because its columns form an orthonormal basis. Okay. Also, because of the way the Gram-Schmidt process works, the ith column of A ends up being a linear combination of only the first I columns of Q. Right? Remember the way we construct the Gram-Schmidt process, at each step we just use the vectors we've used up to that point. So the first column of A is related only to the first column of Q, the second column of A is related to the first and second column of Q, and so on, and therefore the vice versa is also true, right? So, but this tells us that we can in fact look at A in a very interesting way, and here it is. So under these conditions, where A is invertible and Q is the orthogonal matrix obtained from it by using the Gram-Schmidt process on the columns, we start from the matrix A, and we can look at it as a series of column vectors. Okay? And now I can write A as the product of my matrix Q, which I'm also going to see as a set of column vectors, times some other matrix. Well, let's try to figure out what this other matrix should look like. Well, let's look at the first column of A, right? Now, on the one hand, A1 should be equal to the dot product of this column, this row vector that corresponds to Q, times the first column, right? But what should go in that first column? Well, remember that because of the way the Gram-Schmidt process, Q1 is related only to A1 and A1 is related only to Q1. So whatever goes in that column will have some number in the first position and zeros elsewhere. Now, same idea if I look at A2. A2 is on the one hand obtained as the product of that same row times the second column of this new matrix. But on the other hand, A2 is related only to Q1 and Q2, right? And therefore, whatever goes into that column vector will have only some numbers in the first two positions, but not in the remaining ones. Same idea for A3. A3 will correspond to the product of the Q matrix times a column vector, which really will only have numbers in the first three positions, but everything else should be zero. And the same for the other ones up to the last one, which will also have the same property for the last column. So if we think of, now again, this may be some, again, a thinking process that you may want to review in light of the Gram-Schmidt process, review how the Gram-Schmidt process is done to convince yourself that this works. Once you've done that, what have we actually achieved? What we have achieved is the fact that every invertible matrix A can be written as a product. The product of what? Well, the product of an orthogonal matrix Q, namely the one obtained from it by using the Gram-Schmidt, plus of course normalization, and an upper triangular matrix. Notice that the matrix on the right hand side is an upper triangular matrix. So, and this is traditionally denoted by the letter R, where R stands for right hand side because we're multiplying this matrix on the right hand side of Q. Okay. Well, this is an interesting factorization for a number of reasons. We're not really going to use it that much. I'm just bringing it up so for you for general knowledge. We're going to see maybe one or two examples of how to do this factorization. But it is an important factorization because it tells us that every invertible matrix can actually be written as the product of an orthogonal matrix, and we have just said that these are very nice matrices, plus an upper triangular matrix, which is also a nice matrix on its own, in the sense that, for instance, the determinant is easy to compute, the eigenvalues are easy to compute, and all kinds of other things are easy to do because of all the zeros. So it is a factorization that comes in handy in a number of situations, and this, in fact, has a very boring kind of name. It's called the QR factorization of a matrix A. Again, it takes its name from the symbols we use to denote the factorization. And again, it's just a little curiosity for now, but I do hope that you'll be able to use it, if nothing else, as an exercise to understand a little bit better about these orthogonal matrices and how we work with them and with other matrices.